So we are now starting our Q&A session. I must first share my impression about our session. I think that such diverse range of topics, different from study of microalgae diatoms to quantum computations to interfacial fluid mechanics, I think it's quite amazing and even inspiring to see the unity within this diversity. So maybe we can start, yeah. Okay, let's start with you.
I want to thank you all for a brilliant presentation. My question is for Ms. Ozlem. You provided a number of qubits that's required to break RSA. Mm-hmm. I can imagine that compared to a conventional bit, a qubit has way larger degree of freedom. But is the number still so low? What is the computational understanding behind that number? Thank you.
So I think, that falls into, so that's outside of the scope of my work, but from the knowledge I have from the literature, I think if they are noisy, it would take about, maybe 10 million qubits, but when we say these are the 10 million available qubits, but then they need to be error-corrected qubits, right? So it would probably take more than 10 million qubits to be able to break RSA. So the number is low as, so the 4099 qubits that I mentioned are just stable qubits, like actually what a universal quantum computer would have, and at the moment we don't actually have universal quantum computers. But from my knowledge, I think Harvard University just announced that they're a quantum computer with around 48 physical qubits, which is fully error-corrected qubits. So I believe they're heading towards that direction. But I think in terms of, can we break RSA today with what we have? It's probably a no, because IBM only has a quantum computer about 400 qubits that are just error-corrected but not stable, still noisy, sorry. And they will have 1,000 by end of this year, so it's still a long process, I think.
Thank you.
Thank you. Please go ahead.
Hi, I've got a question for Julijana. I wanted to ask, saying when you had the AFM measurements at the different conditions, I was curious to understand why the highest measurement you got was when it was wet.
Yeah, because look, if we have to compare like wet living diatom cell, which contains all organic components inside, as I showed on the first slide, and it also contains like polysaccharide layer on top of this shell. And if we, on the other side, have like cleaned frustule, which contains only those porous silica shell, I think it's quite obvious that those organic materials which are trapped inside the shell actually give rise to those high mechanical performance from the wet living cell. So you have something that is like empty completely, and you have something that is full. So.
Okay, thank you.
Thank you. Okay.
All right, good afternoon, everybody. My name is Erica. I'm from the Philippines, but I study at the National Taiwan University. My question goes to Julijana, because I'm also working with plankton research, and diatoms is actually a diverse group of phytoplankton. So I wonder which species did you use for your study? And because different species of diatoms would have different morphology, do you think that it will actually affect the results of your study?
Thank you very much. Very nice question. Yeah, actually now in my lab, I have about 20 different species, but I prefer to work with these centric ones, like I showed. It's Cocinodiscus oculus iridis species. Why? First, because they're very easy to cultivate in lab conditions. They grow under practically any conditions. They are not so sensitive to light, temperature changes, and nutrient medium, and so on. Then, because of course, they're very nice structure, morphology, multi-layered especially, that's what I've been interested with. But also due to the fact that, for example, if we are having like elongated and very brittle structures, like for example, ulnaria, it is very difficult to conduct mechanical measurements, even using AFM. So actually, it turns out that the indenter in nano-indentation measurements using scanning electron microscopy tends to break. So it's practically impossible to calculate and even obtain some images using AFM and in situ sedimentation on these species. That is why I stick to those centric ones, because they are also large enough. Their sizes ranges from 20 to 80 microns. And yeah, if we are comparing that with like a small elongated species, like around 10 microns, it is very difficult. But still, I think that it will definitely affect. So, because here I mentioned and showed results only based on one example. Of course, I conducted many results during my PhD. And there is difference, definitely there is a difference. Depending on the layer, where are you looking at, even conditions under which those diatoms were grown. So it turns out that even nutrient medium can affect the properties. So it is very important to mention that, yeah, those results that I showed can be applied mainly to the centric species like Cosina discus. But thank you, very nice question. Okay, please.
Hi, thank you for your nice talks. I'm Take, and so my background is in X-ray physics and engineering. And my question actually goes to Ozlem. And so this might be out of your research topic or research scope, but in the world, how Alice and Bob can find the common Charlie, and I'm just wondering whether Alice and Bob have to protect which Charlie actually they are using so that they can protect transfer data.
Yeah, I think so. In the real-world application, obviously, Charlie is well-defined, and I think it will be similar as well. So referring back to maybe telecommunications, like, you know, when you're driving, right, you hop between base stations, depending on your proximity to the end user that you're trying to communicate with. And I think it will be very similar. So you'll be hopping between, you know, repeater stations. And I think if you have two end users, it could be just that they might be, you know, connected to the optical fibers. And I suspect that it will be the interface that we would have to implement based on the proximity, based on where you are. You will be connecting to this Charlie, or it will be going through multiple repeater stations before it gets to Bob. Yeah.
Okay. Thank you so much.
Thank you, please.
Hello, my question is for Julijana. So connecting to the AFM question from before, I wondered if you could give me some clarifying details for your measurements.
Okay, sure.
Just really quick. So your measurements were done in air, is that right?
Yes, right.
Okay, so I guess you did force curve measurements.
Of course, yeah. The results I presented here are based on force curves measurements.
Did you see any capillary effect for the wet diatoms?
Actually, no. Yeah,
No.
I expected to see it, but there wasn't any.
Okay.
Yeah.
Maybe we can discuss.
Yeah, sure.
Thank you.
Thank you. Please.
Hi, thank you so much for all your talks. They were really interesting. My question is for Shiji. Can you say anything about like splashing when things fall into a body of water, not just droplets?
Talk about the explosion, the splash.
Yeah.
Yeah. In fact, the splash occurrence is due to the liquid instability. If the drop impact velocity is high enough, the droplet will be deformed into a thin film. And in that case, the droplet is not stable. And in the front edge of the droplet, and it will be stretched out a single finger, and that finger will be deformed and pinched off. And as a result, the smaller droplet will be generated in the right direction, that is a splash. Yeah.
Thank you.
Thank you.
Hello, another question for Shiji. So I'm interested in the simulations you ran, right? Some of the results you showed were experiments, some were simulations, some were maybe like little analytic models of what you learned. So what forces are included in the simulation? I assume you have to have gravity, like surface tension. And could you, explain a little bit more how the simulation works?
In fact, I did some simulations and using the commercial software that is COMSOL and Fluent that are technical to solve this kind of problems. And the forces included in the governing equation, that is the inertial force, surface tension force, and gravity. In fact, all of these three main important forces are included. But in fact, the gravity plays small role because of the large role of the inertial force and the surface tension force. Yeah, the dominant force is the inertial force and the surface tension force.
Okay.
yeah.
Well, and so is the simulation like, I guess, discretizing your droplet, or is it like a surface?
Yeah, like a surface.
Okay.
Yeah.
Okay, cool.
Yeah. Thank you.
Please go ahead.
Hi, my name is Arthur, and I'm a PhD student in quantum computing in the National University of Singapore. And so naturally, my question will come to Ozlem in the background. In your analysis for the repeaters, I was wondering what kind of noise sources were you considering, like both in the state preparation and the measurement outcomes, because I assume you always face noise and infidelity in the states that you recover. So, yeah.
So in terms of, I think phase noise doesn't affect us when we are actually encoding in the photon number basis, which is a bonus. But yes, there are other noises. So for example, what we consider is the loss that we would get from the optical fiber that we're using, which is about 0.2 dB per kilometer. And in terms of the state preparation, obviously, for high dimensional states, it's harder to say. Like if I encode the states to higher numbers, I don't really know because the sources don't exist. Or to implement it, you really need a very hard experiment. But we actually did our protocol. The simulation shows the protocol using single photon states, which is already existing anyway. So there's the efficiency of the single photon SPDCs. Also, in terms of detection as well, so in Charlie's station, we have the single photon detectors. We assume that they have to be a number resolving detectors, so we need it to be up to 2 photon level. And there are some dark counts associated with the detectors as well. And the most common choice that we had was SNSPDs because they are the state of the art, so they have to be cooled down to cryostat temperatures. So dark count rates were about 10 to the minus 9 in terms of probability, not hertz, because if it's hertz, like it's a hero experiment, oh my God. But it is in terms of probability, which is what other people also use. And also the efficiency, I think the efficiency that we assumed was around 95 or 90%, which is something that you can easily achieve with SNSPDs, yeah.
And just one more question, if I may, on the entanglement swapping procedure. So I figure like you have to do some processing or so get some gates on the information that you collect. Do you assume any noise in these operations for these?
No, actually, you don't have to because we're encoding onto photons. So the gates that we use are actually optics. So in this case, we would have to use beam splitters. So you would interact the two states coming from Ellis and Bob using a 50-50 beam splitter, which is pretty good coding. There's nothing that we need to assume about that. But yeah, in terms of entanglement swapping, all you have to care about is just the 50-50 beam splitter and the photon number resolving detectors.
Thank you.
Yeah, please.
Hello, I'm Cheryl, and I'm studying ecology at NTU in Singapore. So I was thinking, I have a question for Shiji. I was thinking about the drop impact in terms of like irrigation or like raindrops affecting the ground, and which might be permeable, and because of that have different impacts in terms of like when there's desertification or like when this impact the soil and implications on flooding or the crops as well. So I was wondering, when you're thinking about your drop impact, the surface, other than roughness and angle, do you consider like other properties like perhaps permeability?
Yeah, in fact, this is a very good question. The impact incline angle and the surface permeability can affect the impact outcomes. And for the incline angle, in fact, it is observed or it is already validated that the impact process is governed by the normal Weber number normal to the surface. And for the surface properties, such as the roughness or the permeability, it can affect the maximum spreading. And it is a very important topic because for the rain droplet, if the raindrop is acid and the rain droplet maybe penetrate into the porous architecture outside, and it may cause erosions. So it's also important to understand the mechanism and understand the depth of the porosity inside the surface.
Thank you.
Yeah, thank you.
Yeah, please.
Yeah, so my question is to Juliana. So I'm David Azulay from the Hebrew University of Jerusalem in Israel. So my question is about the light intensity distribution analysis that you did. So it was like all theoretical, or you did actual experimental
No, it was
measurement?
completely theoretical. Now we are working on our experiments because it took us some time to prepare the setup and everything. So yeah, it was completely numerically, except for spectra that we collected from individual cells.
And so if you're planning to, can you explain a little bit on the experimental procedure? That
Unfortunately, I cannot. Yeah, because I'm not an engineer, so I'm not preparing like a setup, fabricating it all by myself. Yeah, I cannot.
Perfect, thank you very much.
Thank you. So, no more questions? Oh, okay.
For Ozlem, from what I understood is that the novelty of your work is that Charlie counts the number of whatever they're called.
Photons,
Can you explain like more intuitively why that's better than the other protocols that are around?
Yeah, so in fact, because we're encoding the keys on the number of photons, the states effectively becomes a superposition of different number of photons. And the moment that, Charlie basically counts the number of photons, the remaining state between Alice and Bob becomes also in terms of number of photons. And that's why it's important that we do it in that basis. So there's something in quantum mechanics and also in maths, which is called Schmidt decomposition. So when you encode your keys onto a basis, the natural basis that you need to perform a measurement would be the basis that you chose. Yeah.
Thank you.
Okay.
Right.
Yeah.
My question is to Shiji.
Yeah.
How do you actually generate those droplets, and what's the limit of your droplet size?
In fact, it is a very simple way. Just we use a pump and a needle, and just set an infuse rate for the pump. And when the droplet size is large enough, the gravity will overcome the surface tension that is attached to the needle. And after exceeding the gravity force, the droplet will fall down, and the droplet is generated. That is the macro droplet. Yeah, it's pretty simple.
Okay, so what's the limit of the size?
In fact, for the pendant droplet method, the limit size ranges from 1 microsecond to 3 microsecond in radius. But also it depends on the surface tension and the liquid viscosity. But in general, it is micro-sized.
Okay,
Yeah.
thank you.
Thank you.
Thank you. No more questions? Yeah, I think that brings us to the end of this session. Thank you very much for very interesting questions, and I really hope that you enjoyed it. Thank you.